Okay, YouTube, in this series of videos, we're going to be exploring modeling data using exponential growth and decay models, some logarithmic models, maybe some linear models, but basically modeling data with some sort of function. And we've been focusing on exponential and logarithmic functions. So in this video, we're going to look at exponential growth and decay, and we're going to define it basically thusly. We'll go ahead and get started by looking at what we mean by exponential growth and decay functions. So we get this f of t. It's kind of hard to read here, so I'm going to recopy this. We say f of t, where t is kind of like time here. Is equal to a with a subscript 0, and then it says e to the kt. And then we also express this as a is equal to a with a subscript 0, e to the kt. So these are basically equivalent statements, and one thing that I want to write right here basically is this. We could express this as a equals p e to the rt. So in this general instance, we're going to say that these two models that you see right here, these are growth or decay models depending upon the value of k. But what I'm going to say here essentially is that they're the equivalent of what we've already seen before. So what we're going to say is, in general, we can say that the kind of the amount of something at a time, is equal to the initial amount or our principal amount. So I'm going to write this here: initial amount. I'll put that in parentheses times e to the r, which in this case is k, which is our rate. And then I'm going to say times time, and I'm going to kind of sneak in the time right there. But basically, this is always going to be our growth or our decay model. And so let's write a few things here. We say A0 is the initial amount. That's one thing we want to write here. And with respect to that, like we could say, kind of say notes here. A0 is the initial amount. Let's do this. Let's say that we want to find our amount of something at a given time 0. We could say that this is equal to a sub 0 equals, a sub 0 times e to the k 0, which gives us a sub 0 times e to the 1, which is a sub 0. So in other words, what we're saying is that this is always what we start with in an exponential growth situation. Also, this we would say that k is our rate and t is our time. Okay, so these things basically we'll want to note those here. Actually, I'll put a line here, a line here, and a line here, and this was like a subclause of the first one here. So basically keeping track of these things. So with respect to exponential growth or decay, we'll take a look at this. We say if k is greater than 0, if k is positive, okay? In other words, if you have a positive rate, then the function models the amount or size of a growing entity. And so what we can see here is exponential growth if k is greater than 0, or we could say rate is positive. And if that's the case, we can see that at time 0, which really is equal to right here, we can see that we're starting at some initial amount and then growing exponentially over time at some rate k. And if we have a k that is less than 0, we say that is negative. Okay? The function models the amount or size of a decaying entity. And so we see that at time 0, again here at time 0, we can see that the amount here, we can see time 0, we get a0. We get the amount at time 0, and then it's decaying by some rate k here over time, but never quite getting to 0. So we say sometimes we need to use given data to determine k, the rate of growth or decay, and then after we compute the value of k, we can use the formula a equals a sub 0 equal or times e to the kt to make predictions. And this idea is illustrated in our first of two examples. So we're going to take a look at an example here, but basically this formula that you see right here, just have solace in the fact that it's the same thing that we deal with here. We have a rate, a time, and an initial amount of something. So in this first example, we're going to look at a growth example. And so reading through this here, we say that in 2000, the population of Africa was 807 million, and by 2011, it had grown to 1,052 million. So we can see that it's gone up here over time, okay, in this 11-year span. It says use the exponential growth model a equals a sub 0 e to the kt, in which t is the number of years after 2000, to find the exponential growth function that models the data. So here's the deal. We're going to look for a model and we're going to write down our knowns. So in terms of our model, let's start with this. Our model is what we're going to be writing in this form here. I suppose we could write the amount equals our initial amount e to the kt. And the book uses a sub 0, and some texts use this here. But basically we have a rate, a time, and an initial amount. And so it says right here in 2000 the population of Africa was 807 million. So what we're going to say is our initial amount. I suppose our A0 is equal to 807, and we'll just do this in millions here. And it says by 2011 it had grown to 1,052 million. Now that's going to come in handy here. But one thing I want to point out here is this. Another thing we want to mention here is that t equals 0. Let's write this right here. T equals 0 represents the year 2000. And so in this case, we would say that t equals 11 is 2011. Okay, and that's going to be an important fact as we express this here. Not with 2011, but instead with 11. Okay, so we want to find this model. Here's the secret. Basically, what we're going to do is we're going to plug in what we know already. And so in this case, we say, well, what do we know? Well, we know the initial amount was 807 million. So that's our P. Do we know K? We don't know K. And so this is my point here. We're going to have to find K. But do we know T? And so the weird thing about it is this. We have kind of a time and a population combination. So you got to recognize something here. Every ordered pair in this function is an input of time and then a population. And so this is certainly an x and a y if you want to look at it that way. But what we're saying is 11 years after 2000, that is in the year 2011, we knew that the population was this right here. And so what we're going to do is substitute, if I can spell here, substitute in for our A and our T. And so what we're going to get here is a model that when we substitute these values in, we say this A that we get over here, amount, we say is 1,052. And our initial amount was 807, so that goes in for our P here. We have times e to the power of k times t. Now k, I'm going to put as k because we don't know k, we need to find k. But what I do know is that time here would have to be 11. And so basically what we're saying is we were told the initial amount and we were given a combination of time and population. And so knowing all of these things, and the only thing we don't know is this k here, it means that we can go backwards and solve for it. So I'm going to make sure that I get my calculator on here, and you'll want your calculator as well. But the first thing we're going to do is isolate this base e. So we're going to divide both sides of this by 807. So we'll get some, I guess, rational value over here. We get this. I'm going to kind of carry it up over here. We get 1,052, 807. So I'm going to leave that way for now, is e to the, and I guess this would be 11k. And so now if we take the ln of both sides, that's the interesting thing here. If we take the ln of both sides, these would still be equal, but we get e to the 11k on the right side where these cancel out and we get left with just 11k. And on the left side we get this ln of 1,052 all over 807. And so what I'm going to do is I'm going to take ln of 1,052 over 807, and I'm going to take this 11k and I'm going to divide both by 11 here. And so I'm going to say that k, we're going to write this and we're not going to lose it, is approximately equal to, we're going to go out 4 decimal places here. But basically, let's type this in here. We get the ln of 1,052 divided by 807, which looks brutal, but you know, your calculator's here for you. Oh, we want 807, not 07. So 807 and parentheses. We're going to divide all of that by 11. So making sure we use parentheses wisely here, we 0.0241. So approximately 0.0241. And the reason why I say go out 4 decimal places here, let's write this here, 4 decimal places for any rate. The reason why is because if you change this back into a decimal, this is a 2.41% positive growth rate. So what we've just discovered here is our k, and what we also know is our initial value. And so what I can say is this: we can always write the model if we know 2 things, the initial value and the rate. So we must have the initial amount, we're going to refer to this in the book as A0, and rate, K, to write our model. Basically, once we have these 2 values here, we're going to say that our model is A equals our initial amount, 807. Let me write that 7 again. E to the rate, which is 0.0241 times time. And what we could say is this model right here, I got to put fireworks around this right here. It belongs right here. Put it right here on your paper where it says model. Basically, we can use this to start making predictions now. So we could say that this is some exponential model that has this rate, started at this amount, and went through that ordered data pair that we knew. By which year will Africa's population reach 200 million, or sorry, 2,000 million or 2 billion basically. So 2,000 million, what we're going to do is we're going to plug this in for either time or population. And in this case, they've given us a population value or a y value. So with respect to our model here, what we're going to do is, I'm going to borrow a little space here, we're going to plug this in for our population value and we're going to solve for t. And so what I'm going to do is I'm going to get a new canvas here. Let me see if I can open one up. We have this. Our model is 807 e to the, there we go. We have 807 e to the 0.0241 time. And what we're plugging in here is 2,000 million. So we're going to plug in 2,000 for our population. And so solving for this here, we're going to divide both sides by 807. So we get this expression here. So now we have 2,000 807ths, 807ths, is equal to e to the 0.0241 time. So now we're going to take the natural log of both sides. I'm going to cheat a little bit here. I'm going to write ln of both sides. And so we get this. We get the ln of 2,000 over 807 is equal to 0.0241 times time. So now all that's left to do is divide both sides by this 0.0241. So 0.0241. We'll go ahead and divide this out, and we get time is equal to this exact value right here, exact value. But because we want a time, a number of years after 2000, what we're going to do is we're going to get this on a calculator. So clearing this out, we say the ln of 2,000 divided by 807. All of that, I guess I need a double parenthesis there, I put too many, but divided by 0.0241. And what we're going to get as a time value here is 37.7. So I'm going to write approximately 37.7. We measure time in this problem here in years. So to answer this question, we say 2037. This is the year that we'd want. We want the year 2037 and 7/10 that we're going for here, when the population should reach 2,000 million or 2 billion. So in the next video, we're looking at an example of exponential decay. Cheers.